Welcome to Chemistry 111. What we have today is we're going to finish looking at practice test 4. Reminder, our actual test 4 will be in Odom at 7 p.m. on Thursday. I guess we have enough time. We could easily take it during a class period, but the problem is then reserving a class room that's big enough to hold everyone in here. Now, please note if 7 p.m. is a bad time for you, we'll have plenty of opportunities. Today is about looking at the practice test, quick review of what all is going to be on the test. And then for the rest of the semester, which is not that much longer, it's just going to be various review, and it's a kind of student-led to some extent. You'll tell me what I'll try to you tell me what you need to work on. And like, hey, I'm still struggling on this assignment. We can go through some of the old homework assignments, try to finish some of the difficult problems that maybe some people have been looking at. Or I could just generalize all the material again, because I may not even be recording those lectures, because it's just going to be essentially a spasmodic reviewing of everything we've got. I can break it down into small little snippets, but for the most part, it'll be, hey, a little bit here, a little bit there, a little bit here, a little bit there. I mean, because we'll have gone through all the material that we need to have covered. Don't forget, there is a homework assignment due tonight. It's like, what, 2 readings, learning curve, and chapter 10 homework. Remember, the reading is the only thing you can't go back for, so make sure you do that. But everything else, you can turn in a little bit late. With that in mind, we'll go ahead and get started. See how it's going. Now, quick reminder, last class we had finished things relating to thermodynamics. So this last 10 or so problems will be relating mostly to the gas phase chapter. Now, we have a variety of different questions here, but the first one, tungsten hexafluoride is one of the heaviest gases. It's often used in the formation of circuit boards and semiconductors. What would the density be for WF6 at 25 degrees in 1 bar? So the equation we need is the one that relates molar mass to density. There is only one equation in this chapter that has that, and that's the one that says density is equal to pressure times molar mass divided by RT. It works in the fact that where density is our moles over grams over liters, and we're then using moles over volume and the molar mass to give us our density. So I've stated right away that pressure is 1 bar. So that's going to tell us what R is. R would have to match the units, so 0.08314 bar liters per mole Kelvin. And temperature is 25 degrees, meaning it's 298 Kelvin. Can never use Celsius. Now, the only thing we're missing is our molar mass. The thing we're missing is our molar mass. So, tungsten hexafluoride, we have to look up what is the molar mass of tungsten, what is the molar mass of fluorine, and that's something you can easily get from the periodic table. Tungsten is 183.84. 183.84. And fluorine is essentially 19. 18.998. Most of these numbers you could probably round to some extent. Now, because there's 6 fluorines, you have to multiply that 18.998 by 6. The molar mass is, get some clear from the molar mass is 297.828 grams per mole. At this point, it's just plugging into this equation and evaluating. So 1 times 297.828 divided by 298 and divided by 0.08314. You do that, you would get a density of about 12.02 grams over liters. 12.02 grams over liters. So the correct answer for that one was A. It's a pretty heavy, it's pretty dense gas-wise, but it's still much, much lighter than water. That'd be like 0.012 grams per milliliter. So everyone knows that breathing helium raises the pitch of your voice, makes you all squeaky. A few people realize that if you breathe in argon, it will lower the pitch of your voice. So you'd get a deep baritone voice. Comparing 2 balloons, one helium, one argon, stored at the same temperature, 25 degrees, how much faster would a helium balloon go flat compared to the argon balloon? So this one is just the rate. We're saying the root mean squared velocity of 1 versus the root mean squared velocity of 2. Well, all things said and done, the simplicity of this is you're going to take the molar mass of the second one divided by the molar mass of the first one and square it. Molar mass of the second one divided by the molar mass of the first one and square it. So argon on bottom, helium on top. You got to look up what is the molar mass of argon. Not too tricky. The hard part is to remember to square it, not square it, square root it. So argon is 39.948, essentially 40. And helium is 4.003, essentially 4. Doing this, there should be a number that's greater than 1 when it all said and done. So you get something like 3.159 times. So this means if I had 2 balloons, if I had an argon balloon and a helium balloon, and I just left them out, the argon balloon, however long it might take, say it takes a week, the helium balloon would take 3.15 or essentially 3.16 times faster. So you take your number and you divide it by, what the heck happened? Take your number and you divide it by 3.16. And that would be how much faster we're looking at. So that was those 2 questions. So this one, we're comparing these things together. And this one says density. Those are the weird equation ones, but there's usually a dead giveaway that this is what we're looking for. Okay. 50 grams of unknown gas has this much volume. And the pressure is 1 bar and 0 temperature. So what is the molar mass? So this is another reiteration of that first equation. Density equals pressure times molar mass over RT. So I'm given 50 grams, and that's a mass, a volume of 17.71 liters. Pressure is 1 bar. Temperature is 0 C, which means 273 Kelvin. Okay. Now for this one, we're rearranging this equation to say density times RT over pressure is equal to molar mass. But the first thing we need to do is find density. Density is a mass divided by a volume. So density is going to be our 50 grams divided into 17.71 liters. So doing that would give a density of 2.82 grams over liters. Plugging that into there, we're going to have density 2.82 times our R, 8314, times our T divided by 1, because it's pressure of 1. 8314 times 273. Our molar mass is 64.0. Now, am I going to ask you what the molar mass, what the compound is? No, I'm not going to ask you that. I tried that once, and it ends up being too darn confusing because there's too many possibilities. But having a 64 molar mass, that is probably SO2. SO2, and that sulfur is 32. Each oxygen is 16. 2 oxygens add up to 32. 32 plus 32 is 64. That is answer B. Please note, however, let's think about this. When dealing with a molar mass, what is the lightest element? The lightest element is hydrogen, which has a molar mass of 1 gram per mole. So is there going to be any molar mass that is less than 1? The answer is no. So A is right off the bat. Think about, we're dealing with a molar mass. What if I had a molar mass of 1,000,000, something like that? That would probably be very unlikely for a gas. So just think about that. Now, 19. This is Dalton's wall partial pressures. It seems difficult, but once you know what you're doing, it's really not that hard. The first space station, Skylab, used a molar ratio of 70% oxygen and 30% nitrogen at a pressure of 5 psi. What is the partial pressure of oxygen in psi? So, say the total pressure of 5 psi is made up of some percentage of oxygen and some percentage of nitrogen. The total pressures of those two add up to 5. So if 70% of this is oxygen, 70% is oxygen, how do we find out the pressure of oxygen? Well, the long story short is if they got it, it was 5 psi times 0.70. Doing that, it's like, I'd like to say it's 3.5 psi. 3.5 psi. meaning nitrogen would have to be 1.5 psi. When you add those two together, you get 5. But it literally is, that one was literally supposed to be that simple. However, you have to understand percentages and what it means to be a mixed gas. Okay. Number 20. Decompression sickness is caused by rapid expansion of high pressure dissolved gases within the body. If a diver rapidly ascends from depth of 200 feet, the pressure will have changed from 101.5 psi to 14.5 psi. So essentially you have gas in the body, in the bloodstream, in everywhere. And a diver and all those gases are going to undergo ideal gas law. So as you go down in the depths, your pressure will change. I think it like doubles every like 10 feet or something like that. So if you're going down really deep, you're looking at a great change in volume, and your body needs to give a chance to accommodate that. The gas will expand, the gas will leak out and have a chance to escape, but it's a slow thing. It's going to effuse through tiny little microscopic pores that it's going to expand and escape and effuse, but it takes time to do that. And so so you can't just rapidly ascend from the bottom of the ocean to the surface without dealing with that. So this one is not an ideal, well, it's an ideal gas equation, but it uses only Boyle's law. We don't use the full equation. This is one where we set up the 2 pressures and 2 volumes. This is simply put, P1 V1 equals P2 V2. We don't even need to change the units. We can leave them the same because pressure will cancel out pressure. 101.5 psi. P2 is 14.5 psi. The volume one is 5 mils. So V2 is going to be what? So I want to just you set this up. 14.5 times V2. So what do we got to do? We got to divide both sides by 14.5. 101.5 times 5 over 14.5. It's all going to be V2. So if that's PSI, and that's PSI, PSI and PSI cancel, and we're left with units of volume in milliliters. So what happens? The volume is now 35 mils. 35 mils. So the correct answer was B. It's increased, not a huge amount, just by a factor of 7, but when your blood vessels aren't meant to hold that much volume, it can be very painful and could cause an aneurysm. If you get like suddenly the air bubble goes up to your brain, and then suddenly your brain is starved of oxygen. Okay. One was a van der Waals equation where you didn't actually have to utilize the equation, but you had to understand the equation. Van der Waals gas, the pressure term P plus N squared A over V squared, and the volume term V minus NB. The B accounts for what aspect of the gas? Remember, N is moles, V is volume, P is pressure, T is temperature. So A and B. We're dealing with, to try to adjust this, we're dealing with the interactive forces and the size of the gas. Well, the B, since we're moving from the volume, deals with the actual atomic size of the gases. Deals with the actual atomic size of the gases. So the correct answer was A. The constant A will deal with its repulsive forces. How well do these gases interact with each other? The interactive or repulsive forces would be constant A, but constant B deals with the atomic size. Easy one. They have a lot of gas stuff. Avogadro's law states that volume is directly proportional to what variable? Once again, I'm not going to ask you to name the laws on this one. I don't have 25 questions. I have 20 questions. So 5 less questions to work with. But Avogadro's law is volume is directly related to the moles of gas. The reason I asked that one and not Boyle's and Charles is hopefully you remember Avogadro's law because it relates to Avogadro's number, which relates number of atoms to the concept of moles. '23 is another one where you have to relate 2 variables. This one relates Charles' law. Refrigerators work via forced compression and expansion of gases to transfer heat from inside the fridge and out the back through heat exchange pipes. Gas is allowed to expand from high pressure hot region at 800 torr and 60 degrees C to a low pressure region at 600 torr. How many degrees Kelvin would the temperature drop? So this one is actually quite a bit more challenging. This one relates, actually, this isn't Charles' law. This is one we didn't really learn, but called Gay-Lussac. But this relates pressure and temperature in much the same way as volume and temperature. Pressure P1 over T1 equals P2 over T2. Essentially, we're saying that PV equals nRT, and we're getting the variables to one side and the constant on the other, and setting 2 things the same. Once again, we don't have to change the pressures. 800 torr is okay. However, we have to change the temperature into Kelvin, because otherwise we're not going to get as big of an effect. Because this is addition instead of division when it comes to conversion. So 60 degrees C will become 333 Kelvin. So our question is, what is T2? Question was T2. And then it's how many degrees Kelvin did the temperature actually drop? So it's a 2-fold, maybe 3-fold trickiness to this problem. So if I have P1, T1, P2, and not T2, how do I solve for T2? Well, normally I would multiply T2 to the other side, and then these two. So my equation now looks like T2 equals P2 times T1 over P1. So that in mind, 600 torr is our P2. Our 333 Kelvin is our T1, all over 800 torr as our P1. See, torr and torr cancel out. So our T2 is 249.75. So how much did the temperature drop? How much did the temperature drop? We're going to say 249.75 minus 333. It drops by 83 and a quarter. So 249. That right there is below freezing. And what's allowed, so, and then that 249 can then absorb heat from the fridge and warm back up so it can be put through the system again and recirculated. So the question 83.3 Kelvin is our answer. A. 24. Last two. 24. The recent news, scientists found a molecule on Venus that may be indicative of life. If on Earth, 1 mole of gas takes 22.4 liters. That's the volume of 1 mole of gas. What volume would that same mole of gas take up on Venus with its ambient temperature of 464 Celsius and surface pressure 92 bars? This is our first PV equals nRT problem. We're saying if N is 1 mole, what is our V given the fact that temperature is 464 Celsius and pressure is 92 bars? So the first thing we got to do is change our temperature. 464 plus 273 is 737. 37 Kelvin. So it's much higher temperature, but much higher pressure. Much higher temperature, so much higher pressure. Rearranging this, we say V equals nRT over P. So let's plug it. We have 1 mole of gas. I'm going to use ideal gas 8314 times 737 divided by 92 bar. Okay.
Dr. Andrews.
Yes.
Why are you using 0.08314 on this when it's not energy? Or is it energy?
Oh, no. Okay.
Because I thought we were supposed to be using 0.08206.
Okay, so 0.08314 is bar liter per mole Kelvin. 8206 is atmosphere liter per mole Kelvin. And the one you're thinking of is 8.314, which is joules per mole Kelvin. This is actually a rearrangement of this. Sorry, that's kind of off. It's a rearrangement of this, and that a joule is equal to like 1 joule. Let's say there's 100 joules in 1 bar liter. Yeah, there's 100 joules in 1 bar liter. So this is the one we use when thermodynamics, when we deal with Q and delta H and stuff. And this is, oh God, I've totally goofed that up. This is the one we use with Q and delta H and all of our thermodynamics. And this is the one we use with one of these two. One of these two are when we're dealing with pressure, volume, and when we use with gases. So now, in all actuality, the one I use depends on the units. But in all actuality, if you screw up and use this one, your number will not change by any significant amount. And I will do that. I'll do it both ways real quick just to show you how much it won't change. It will change it by a rounding error. And depending on which one I favor, depends on from year to year. Because some years I do more units with bars. Sometimes I don't bother and I just leave it in atmospheres. I like bars better than I like atmospheres, but sometimes it's just easier to leave it in atmospheres for simplicity's sake. But okay, so this one, if I do it like this, 0.08314 times 737 divided by 92. If I do that, my 1 mole of gas takes up 0.666 liters. 0.666 liters. Now, hypothetically, if I'd used the other R, I would have got a number that's the other option would have been 0.657. 6574. So if you had used the wrong one by mistake, for whatever reason, you would still get close enough to the right answer that you could say, oh, it's still D. I must have done a rounding error. I must have screwed something up. But it didn't change it by enough to, I mean, I used to try to trick my students up by putting two answers, that one where they use the wrong R, but I'm not trying to do that anymore, mainly because it's just too close. There's too many places where student could have rounded here or rounded there, and then they get the wrong answer, not because they used the wrong R, but just because maybe they're slightly sloppy on the math. And they did it stepwise instead of all at once. So I've gone away with trying to do that. So if you use either R, you should get close to the right answer. But as I said, 657 or 666, see what difference. It is like a 1% difference. It really is. It's like maybe 1.3% difference in the answer. And as I said, that's too close in the answers. Even Achieve, I think, allows you like 2 or 3, if not 5% error in your numbers. So that if you rounded too much, you could still get the right answer. Which is why I've stopped trying to trick the students that way. Hopefully that answered your question. The last question here. Gas in the lower troposphere has a molar density of 22.4. If gas would travel to the upper troposphere or even the tropopause, parts of the atmosphere, it would expand to 90.6 liters under external pressure of 200 millibars. So what would the temperature have to cool down to? So we're given volume is 90.6. Pressure is 200 millibars, which is the same. It's like millibars is to bars as milliliters is to liters. So that would be 0.200 bars. once again, 1 mole of gas, and I'm asking, what is the temperature? So for this last question, it's just another iteration of the PV equals nRT. So there's a PV over nR equals temperature. So 0.200 bars, 90.6 liters. N is 1 mole. And because this is bars, I'm using the 0.08314 bar liter per mole. And that would give us our temperature in Kelvin. So 0.200 times 90.6 divided by our R. You get the temperature would be 217.9 Kelvin. I'm not sure if I need this in Celsius, but if it was in Celsius, it would be negative 55 degrees Celsius. So up in the high atmosphere, right before we have the atmosphere, the stratosphere, we have the stratopause, we have the troposphere. If I remember the right, troposphere is where we have all the ozone. That's where we're blocking a lot of the sunlight. Tropopause is right before it gets to the next layer, where it's like almost at the outermost layer. So what does the temperature cool down to? And so it's in Celsius. So the correct answer is negative 55. So really, really cold. Really, really cold. That was the old exam. That's what I asked from them. So quick reminder, quick refresher of what all's on this exam. We have on here, are grams to moles to grams to some extent. This can be utilized from any place. It can be utilized to go for limiting reactant. It could be used for percent yield, where we have to utilize the actual yield divided by the theoretical times 100. But we go grams to moles to moles to grams. We can go with this from any place. That's where we set up. So if I have equation, I'm going to write A sub A plus B sub B goes to C sub C. If I want to go from A to C, I would have to have the mass of A divided by the molar mass of A, the coefficient A sub A, and then the coefficient of C times the molar mass of C. This is our ratio. If I wanted to go to B, I'll just replace that with B sub B and molar mass of B. So we're going to use that. We can also go grams to moles to molarity, or molarity to moles to grams. Remember, M times volume times molar mass will give us grams. Or we could do grams divided by molar mass divided by volume equals molarity. That molarity is essentially moles over volume. Sorry, I'm off the screen. Then finally, for that chapter, we learned that the M1V1 equals M2V2, that we could utilize if I know the molarity in one situation and its volume, and I know one of the two other variables for the other situation, we can know either the volume or the molarity of the second situation. And that was then utilized with the titration of acids and bases, which we did in lab. MAVA equals MBVB, where at the equivalence point, 1 mole of acid equals 1 mole of base. When they canceled each other out, they have 1 to 1. And so if I know the molarity and volume of one, I can know the molarity or volume of the other. All that was chapter 9. Chapter 10, we looked at internal energy, which was a small, very small part, where the internal energy is plus work. Heat flow is equal to mc delta T. The heat Q equals mcat. Q equals mass times specific heat times change in temperature. We could use that to, if I have the heat and a mass and a temperature change, we could find the C. Or if we had mc and delta T, we could find the Q. Or if we had the Q, the M, and the C, we can find what the change in temperature should have been. Then we had our delta H. Delta H of the action was the sum of the H of products minus the sum of the H of reactants. It essentially, what does delta mean? It means final minus initial. Final minus initial. So you take the products, which is the final situation, minus the initial, minus the reactants, which are the initial. And we also finally had Hess's law. Hess's law just says if reaction 1 plus reaction 2 equals reaction 3, then H1 plus H2 would be equal to H3. That by adding reactions together, I can get a new reaction. The enthalpy of the new reaction would be equal to the sum of the previous enthalpies. So if I had to double reaction 1, I would have to double its enthalpy. If I had to flip around reaction 1, so I subtracted reaction 1, I would have to subtract its enthalpy. Then finally, the last little bit was our ideal gas. We had PV equals nRT. It's our main thing. But we could also have PV equals PV, or we could have any combination of V1 over T1 equals V2 over T2, something like that. But all that's just, that's all dealt with in Chapter 11A homework. Chapter 11B dealt with our density equals pressure times molar mass over RT, which we could look at if we're solving for molar mass, it's density times RT over pressure. All that is, right? And then we had our rate of effusion. Rate 1 over rate 2 is equal to the square root of molar mass 2 over molar mass 1. I will not really ask you to do the root mean square velocity. I will not really ask you to utilize the van der Waals equation of a gas. There's one other thing, and that was Dalton. Dalton just says that the pressure total is equal to the pressure of individual gases, the sum of all the gases. Dot, dot, dot. Total pressure is equal to sum of each individual gas. Those are our big things. Now, as I said, the test is on Thursday. Bring a calculator. This is the one test you absolutely need to have a calculator for. You're not going to get very far without it, even though it's mostly multiple choice. Also, you're allowed to have a cheat sheet. Don't forget, one page, front and back, handwritten. There's not a whole lot of stuff you need to memorize on there. However, one thing I would suggest helps a lot of people is work out problems on there. So I don't understand Hess's law with a spit. So maybe I should work a Hess's law problem off in a small corner of the this. In that way, I can see, oh, how I did it. I don't understand delta H reaction, so I'm going to work out a delta H reaction one somewhere on the thing. And so I can go, okay, this is the numbers I used. This is how it was given on this test. This is what I had to do. So you can hopefully imitate that come test time. So if you're struggling on a particular type of problem, working one out like this on the cheat sheet will be of some use to you. That's what I got for you today. As I said, I may or may not record and make a video for Wednesday's class. We'll figure it out. But come ready with some questions. Like, I am still struggling on achieve for these problems, especially if they relate to the chapters of the test. I mean, so we may have a shortened class at that point, but thank you for your time. I will see you on Wednesday or Tuesday for lab.